Welcome to the Greek Corrosion channel. My name is Mariam. I'm a researcher in the field of corrosion and protection of materials. Chapter 1, Section 5, Basics of Electrochemical Corrosion. Common industrial cathodic half cells in corrosion phenomena. Our reference is shown here. Why are cathodic reactions more significant than anodic ones? 1. Corrosion of a metal, the process of oxidation or loss of electrons, is always supported by a cathodic reactant or an oxidizing agent, which is reduced during the cathodic reaction. 2. Generally, the stronger the oxidation reaction is thermodynamically and kinetically, the greater the corrosion rate becomes. So it's worth noting that for corrosion control in industries, it is beneficial to know the cathodic reactants in the environment. What are pH and pOH? Logarithmic factors. It's very convenient to introduce the pH as a measure of the hydrogen ion activity in aqueous solutions. Also, pH and pOH are related to each other. pH plus pOH equals 14. P represents the logarithmic factor of a parameter and is used in thermodynamics too. For example, the logarithmic factor of equilibrium constant is pK, which is the negative logarithm of the parameter. pK equals minus logarithm of K. pH equals minus logarithm AH plus. pOH equals minus logarithm AOH minus. The product of AOH minus and AH plus equals 10 to the power of minus 14. Common cathodic reactions in corrosion processes. It should be noted that the most common cathodic reactions are reduction of positively charged hydrogen H+, 2H+, plus 2 electrons equals H2, and or reduction of oxygen O2 plus 2H2O plus 4 electrons equals 4OH minus O2 plus 4H plus 4 electrons equals 2H2O. Oxygen reduction reaction. Reduction of oxygen increases the pH of the solution. In acidic solutions, H+ is consumed and water is produced. Here, oxygen is reduced in acidic solution and water is produced. In neutral solutions, oxygen reacts with water and OH- is produced. Here, oxygen is reduced in a neutral solution and OH- is produced. In neutral solutions, E0 equals positive 401 mV versus standard hydrogen electrode, and in acidic solutions, E0 equals positive 1229 mV versus standard hydrogen electrode. Reduction of proton, one of the most common cathodic reactions recording deaerated solutions. 2H+ plus 2 electrons equals H2. Immersed equation, E prime equals E0 plus 59 logarithm of H plus activity divided by pH2 to the power of 1 divided by 2. At the end, E prime equals minus 59 pH minus 29.5 logarithm of pH2. In this figure, dependence of hydrogen reaction equilibrium potential on pH is shown. This equation is plotted in the figure in terms of pH as the variable with pH2 as a parameter. Increasing pH and pH2 causes the potential to move in the negative direction. More negative potential means less tendency for being reduced. Also, dependence of hydrogen reaction equilibrium potential on hydrogen gas partial potential is shown here. The horizontal axis is set to a logarithmic scale. Challenge number 4. How much pressure of hydrogen is required to stop corrosion of iron immersed in a deaerated 0.1 molar FeCl2 solution at pH 3, assuming activity coefficient equals 1, gamma Fe2 plus equals 1. In this figure, dependence of oxygen reaction equilibrium potential on pH is shown. The equation is plotted in this figure in terms of pH as the variable with PO2 as a parameter. The potential decreases with increasing pH but increases with increasing PO2. The latter effect of increasing gas pressure is opposite that observed on increasing the hydrogen pressure for the hydrogen half cell. This follows from the fact that the gaseous species occur on opposite sides of their half cell reactions. Also, this equation is plotted in this figure in terms of PO2 with pH as a parameter. Dependence of oxygen reaction equilibrium potential on oxygen gas partial pressure. Note, the parameter is set before the execution of the package and its value is fixed during execution, but the variable is set during execution. In this table, significant cathodic reactions in industry and their equilibrium potentials are shown. Cathodic reaction, standard equilibrium half cell potential E0 versus standard hydrogen electrode. Variables required for correction of E0 to E'. Oxidation due to reaction to the metallic state. Reduction of copper cation to copper, positive 342. Oxidation due to oxidizing anion radical, dichromates. Dichromate reduction in acidic solutions, positive 1333. Nitrites. Reduction of nitrite in acidic solution, positive 890. Nitric acid reduction, positive 940. In each equation, all species are variables required for correction of E0 to E'. Continuation of the previous slide. Cathodic reaction, standard equilibrium half cell potential E0, variables required for correction of E0 to E'. Oxidation due to H+ ions or water, negative 820. Oxidation due to dissolved oxygen at pH lower than 7, positive 1229, and at pH greater than or equal to 7, positive 401. Oxidation due to change in valence of ionic species, for example ferric to ferrous, positive 771. Note 1. All of these potentials are relatively positive, except for the reduction of water. Note 2. These standard values correspond to 25 degrees Celsius and to the unit activity of the species and need to be corrected for the actual temperature and activities. Nernst equation will be covered in the video chapter 2 section 2. This figure shows ranges of half cell potentials of some electrochemical reactions of importance in corrosion. There are 3 scales in this figure for potential versus 3 reference electrodes. Standard hydrogen electrode, saturated calomel, and saturated silver chloride are shown here. Anodic reactions are shown for silver, copper, lead, nickel, iron, zinc, aluminum. Vertical bars represent metal ion concentration of 1 moli down to 1 ppm. Dash extensions may apply with precipitated and complexing species. The hydrogen and oxygen reactions depend on both pH and pressure of the gases. Values for the hydrogen are at 1 atmosphere pressure. Values for oxygen are for water in contact with air, aerated, giving 10 ppm dissolved oxygen, and for water deaerated to 1 ppb dissolved oxygen. And here, dichromates, ferric ions, and cupric ions with their potentials are shown here. Standard reference electrodes potentials are summarized here. 0 for standard hydrogen electrode, positive 241 for saturated calomel, positive 196 mV versus standard hydrogen electrode for saturated silver chloride electrode. Thank you for your time. Challenge number 5. Please comment down below which slide captured your attention. Slide number 69 or 72 or 75 or 79 or 80.